So thank you, Christina, for the kind introduction. While people are still coming in, let me start by telling a bit about the history of my research that I'm going to present. I've been working with two PhD students, Sjouke and Jorge, and a postdoc, Rolando. And when Rolando joined my team some 5 years ago, he introduced me to distance bounding protocols. Having a background in authentication protocols, I looked at the distance bounding protocols world, and it turned out that they had a very attack-oriented view on distance bounding protocols. There are various types of attack, and the sport is to protect against these attacks. Well, I'm used to having a security property that could be verified. So that set my mind of thinking what is going on in this field and how can we bring it to a more symbolic model, a more symbolic approach, which is independent of particular attacks. We formulated our work some 4 years ago as conjecture, submitted a proposal, hired PhD students on that, and Jorge picked up the task of doing that work, and Sjouke, my other co-author, implemented everything in a current model checker, Tamarin. So first, a very short overview of my presentation. I will have two parts. The first part, I will recap some knowledge that is needed, existing knowledge that is needed to interpret our new results. And then I will come to our results, which is in fact a simplification of current analysis models of distance bounding protocols. And the simplification boils down to doing away with time, doing away with location, and only look at the order of the events in the execution traces of the protocol. So let's first look at the problem of that we are trying to solve. So the problem is that once we introduce electronic means to, for example, open your car, you will be susceptible to protocol attacks that are different from the standard authentication attacks. And if you look at this example, you see a modern car with some guy who has car keys. And let's assume that these keys are passive keys in the sense that they can communicate automatically with the car and open the car door and start the car engine. And the idea is that the car door will only be opened automatically if he is near the car, and the car engine will only be started if he is within the car. And now the idea of the attack that's called a relay attack is that you simply take the messages from the car to the keys and relay them at any distance that you see fit, and you relay the answers back to the car. And in that way, if this owner of the car is in the shop doing his shopping, then the car can be stolen easily by people who collude to relay these messages. So that's the basic idea. And the typical attack here is called a relay attack, which is a man-in-the-middle attack, where the attacker simply forwards every communication to the other party, and in that way wins some distance. These kind of attacks have been proven in practice, not only on cars, also on your smart card payments, where Murdoch Dimer in 2007 proved that you can fool somebody into thinking that he's buying a package of cigarettes, while in fact he is buying a diamond and somebody else is taking the diamond away. So that's also a kind of relay attack, and also a Google Wallet attack that was reported in 2013. And the solution to this relay problem is the development of distance bounding protocols. So a distance bounding protocol is an authentication protocol that has an added feature, and the feature is that it measures the distance between the two parties executing this protocol. So there will be a reader, which is offering a service to a client, and the client has a tag, and only if the tag is close enough to the reader, the service will be offered, the door will be opened, for example. Let's have a look at a very simple diagram to explain that. The reader has this distance d that he requires the tag to be within this perimeter in order to offer the service. And then in a communication with the tag, in the case that the tag is within the parameter, the protocol will succeed after execution in a positive way, while if the tag is outside the parameter, the protocol will fail and will deny the service to the tag. Even if the tag is willing to do something bad, if the tag itself is the adversary, then this protocol should fail with the tag outside the parameter. And another scenario is this man-in-the-middle attack, where we have an adversary who is not a normal user, but he can somehow reach a user outside the parameter and try to somehow use the information from the tag to prove that he is inside, or in fact the tag is inside the parameter. That's also an attack that we want to prevent to happen. If we zoom in onto what a protocol would do, we see that a distance bounding protocol executes in 3 phases. The first phase is to establish some common ground on say the randomness that they share. The second phase is the fast phase, and sometimes there is a third phase, which is exchange of signatures to prove really that somebody has followed the protocol. So the fast phase is the interesting part of the protocol, where we see that there's a reader who starts by making up a challenge, which is probably a fresh random challenge. And this challenge will be sent to the tag in order for the tag to calculate the correct response to this particular challenge. And the calculation of that response will take some time, let's call it tcomp, and then it sends it back to the reader, and in total the whole round trip time will be measurable by the reader because he has set a timer, and he is checking the timer after receiving of the response. Then the reader will, after finishing the protocol, he will accept the tag as being close enough if this delta t is smaller than a certain threshold. And let's see how we can calculate the threshold. There's a very simple law, and that's the law that information cannot travel faster than light. So if we say c is the speed of light, then c times the pure time that the message were traveling, so that's delta t minus the computation time of the tag, and then divided by 2 because it's a two-way message. This will be the distance between the reader and the tag. It's a very simple formula. Unlucky is the case that we don't know the computation time of the tag, and that's one of the problems. So ideally, we want to have this computation time as small as possible in order to have a very simple approximation by simply discarding the tcomp. An attacker could get hold of the tag and overclock it, and letting it run faster than you would expect, implying that the tag would be closer than it is in fact. So this is pretty straightforward. This is in fact the basis of one of the models that has been developed a few years ago by David Basin and some colleagues to prove that certain protocols are satisfying, that there are no distance bounding attacks on them. The model itself is the starting point for our research, and of course it's a few pages of dense math, but I will try to summarize it in one slide. So the model has time traces, where we have events, E, and timestamps, T, and there are 2 more features that you need to know in the model. One is that it considers the distance between 2 agents, A and B. Rather than having the location of the 2 agents, it considers the distance as a primitive notion. And then finally, we have the notion of claim events, a special type of events, apart from the reception and the sending of messages. These claim events, they state at the end of the behavior of the reader, it states that the reader has checked 2 things. One, the authentication is correct, so the response was indeed related to the challenge. And second, it was fast enough to be within this distance d that you expect. So that's the 2 things that are stated in a claim. And formally it states party A has reached its end of the protocol, and it concludes that party B is close enough to him based on the observation of sending the challenge, which is event A, and receiving the response, which is event B. So that's all you need to know of this model in order to appreciate the formal definition that they gave. Of course, I simplified everything as much as possible. And the model of Basin et al. they have the following approach to defining secure distance bounding. So a protocol P satisfies secure distance bounding if for every trace generated by the protocol, if that trace contains a claim event, so it contains a successful execution of the protocol by the reader, then there are instances of these two events, small a and b, and an instance is simply assigning a time point to it. So there are time points ta and tb such that the distance between agents capital A and capital B satisfies this distance relation that I just explained. So this is basically the definition of secure distance bounding. They implemented in Isabelle Hall, and with a bit of effort, they could verify protocols. This is the end of the known things. And so next I make the transition to what we added to this knowledge. And the first observation is that this distance between A and B, which should be smaller than half c times the time difference, this is very symbolic. None of the protocols uses absolute time. They also always use this kind of symbolic time. And the observation that I made is that this symbolic thing leads to a step further in abstraction away of timing, namely replace timing by causality. And causality means the order of the events in your trace. And I'll try to explain the intuition that I have behind the result. So we have a distance bounding protocol, and we have an execution, which is a correct execution, in which a challenge arrives at B, and after that, the response is made up. So this is a standard execution that you would expect. Now, suppose we have a flaw in this protocol, then an attacker would be able to produce this kind of behavior. It could preempt the reception of the challenge and send the response that you would expect before it even receives the challenge. And in this way, if he can predict a challenge, he can predict the response correctly, he pushes the delta t in a way such that the distance is smaller than it in fact is. So this is what I would call early timing. And what you see is there is a violation of the causality what we expected. There's a violation of the causality at the site of B that response is being created after the challenge has been received. We could even push this a bit further, namely, once you know that you can produce your response without knowing the challenge, you could even send the response before the challenge has been sent itself. There's no reason to wait for the challenge to be sent. So this is, in fact, what we call very early timing. And now the idea is that in the third diagram, you see that there is between the sending of the challenge at the A site and the reception of the response, there is no activity of B at all in between these events. And that's the crucial part of dealing with causality in distance bounding protocols. And we have the very simple claim that if there's a protocol with a flaw that allows for an early timing flaw, then it should also allow for a very early timing flaw. And that's, in fact, the intuition behind the whole proof of our methodology. And this also gives us an alternative definition of distance bounding security, which we call causality-based distance bounding. And it states that if we look at all untimed traces that contain some claim at the end of the reader role, then we have three indexes of this trace. The first index, I, relates to the sending of the challenge. The third index, K, relates to the reception of the response. And we see that sending should be for reception, but we also see this index J, which relates to any event of the tag in between I and J. So we only have to require that for every claim, there are instances of A and B, and there must be, in between these instances of A and B, there must be any activity from the tag itself. So that's the formulation that we made. We were able to formulate it as a formal theorem, and the proof is not too complicated. In fact, we cut the proof in two parts. We formulated 7 properties that are relatively obvious in the model of Bayesian, and which are sufficient for us to prove our theorem. So this is the step towards the proof. Of course, you can read it all in the paper. Implementation in Tamarin was pretty straightforward, except for the fact that we had to do quite a lot of abstraction of the protocols itself. We looked at a set of protocols from literature. Most of the protocols with errors, we confirmed that these errors were there automatically by push button technology. Protocols that were correct, we confirmed that they were correct in our model as well, but we found 2 protocols, the threat and the paysafe model protocol, for which we found new attacks just by pushing the Tamarin engine. To finalize, so what we have achieved, we have formulated a variation of an existing property by using only causality, which allowed for fully automatic verification of distance bounding protocols. We provided verification of a set of existing protocols, and we found attacks in protocols paysafe and threat. And in fact, the threat protocol was proven correct by the authors in a different formalism. And we tried to understand why their proof is invalid, and that's because they have a weaker attacker model than what is normal in this field. Okay, thank you for your attention. I'm happy to answer any questions.
So for questions, please state your name and affiliation before asking the question.
Vincent Cheval, INRIA. So I was wondering, is your definition sound with respect to the definition of sound and complete with respect to the definition of Bayesian, or just sound?
It's equivalent to the definition, so it's sound and complete. Okay. For the class of what they call well-formed protocols.
For the class of?
For the class, what is called well-formed protocols, David Bayesian considers only sane protocols, which he calls well-formed protocols.
And so do you have an example of a protocol that is not within this class?
Yeah, for example, a protocol that has a trace that goes back in time. So you do something and suddenly there's an event at an earlier time point. That is not a sound protocol.
Okay.
Yeah, so these are quite I checked them. These are quite reasonable expectations.
Thank you.
Thanks.
So maybe also a quick question from me. You mentioned that there were 2 protocols where you found flaws.
Yeah.
How unexpected were these? Was it exactly the same flaw, or can you give us a little bit more details about that?
They were quite unexpected. So the space-safe protocol is based on, I think it's EMV. It's just an extension with distance bounding, if I'm correct. So I didn't expect them to make errors in that. And the threat protocol, they proved it correct. And they used an existing proof method, but that method was incomplete. That was clearly the case. So that was quite unexpected to find errors in proven protocols.
So maybe we can, we have, yes,
Oh,
sorry.
Hi, this is Robert Lichoff from MIT Lincoln Lab. Thank you for an interesting presentation. So I'm not very familiar with the field, but are these protocols often relying on some cryptographic primitives to achieve causality?
Yeah, the early protocols by David Sjouke 25 years ago, they were based on cryptographic primitive. Nowadays, we look very much at solutions for RFID technology, and as you know, crypto is not easy to integrate with RFID technology, so they often have exclusive OR and simple hash functions.
And was that the source of some of the protocols that didn't?
No.
Oh, I see. So there were other reasons.
They were logical flaws, not of the cryptographic type. Absolutely not.
Okay, thank you.
Thanks.
Hi, my name is Ioana from University of Surrey. Thank you for the presentation, Sjouke. So, in your work, which is very nice, by the way, you have this crux lemma that says that an early send would imply a very early send from the tag sign. And I think that that's perfectly valid in your model, but just an observation that in practice, tags these days receive things bit by bit. And because they receive things bit by bit, then this would not necessarily be the case. So you send me a nonce, as I see the first bit arriving, I send you back the first bit, I receive the second bit, I send you back the second bit, and so on and so forth. So maybe this is some scope for thinking about how, if somehow, say, in your terms you would be modeling bits, then you'd need a different sort of causality to model this type of attacks.
Yeah.
Where in fact I can process the messages as I go along, and therefore an early send does not imply a very early send.
Yeah, I fully agree with your observation. We have two approaches here. One is the approach that if the challenges are sequenced in a sense, as you have explained, then we should have a claim for each challenge response cycle per bit. And in that sense, it may work out with this approach. And the second is that we are hard working on translating our results to a more probabilistic model where we can do statistical analysis. We have some initial ideas, and it will take at least a few months to come with something useful here.
Right. Thank you very much.
Thank you for the question.
Let's thank our speaker.